In a room of 23 people, the probability that 2 of them share a birthday is not 1 in 16. It's not 1 in 8. It's slightly better than 50%. Most people guess the answer is somewhere around 70. Some say 100. A few will confidently tell you 365. They are all wrong by a factor of at least 3. This isn't a trick. There's no fine print. 23 strangers in a room, and more often than not, 2 of them blew out candles on the same day. For the next 8 minutes, we're going to find out exactly why. The problem was first laid out formally by Austrian mathematician Richard von Mises in 1939. In a paper about the difference between a probability you feel and a probability you calculate. The setup is as simple as probability gets. 3 rules, none of them controversial. 1. There are 365 possible birthdays. We're ignoring leap years. It changes nothing. 2. Each person's birthday is independent of everyone else's. No twins, no relatives, no hidden patterns. 3. We're not asking whether someone shares a birthday with you. We're asking whether any 2 people in the room share a birthday with each other. That 3rd rule is the entire trick. Almost nobody notices it the first time, and once you miss it, the correct answer becomes impossible to guess. Now we follow the math, 1 step at a time. Step 1. We ask the easier question first. What is the probability that all 23 people have different birthdays? Person 1 picks any birthday. Person 2 has to avoid it. 364 days out of 365 are still free. Person 3 has to avoid 2 days. 363 over 365. Person 4 avoids 3 days. And so on, all the way down to person 23, who has to avoid 22 days out of 365. Multiply all 22 of those fractions together. The answer is 49.3%. Step 2. The probability that at least 2 people share a birthday is just 1 minus that number, 50.7%, not roughly half, exactly half, plus a margin, with only 23 people in the room. So why does this feel wrong? The answer is not in the math. It's in what your brain counted when it wasn't looking. When you picture 23 people in a room and ask about shared birthdays, your mind does something very specific. It picks one person, usually you, and compares that person to everyone else. That's 22 comparisons, 22 chances for a match against 365 possible days. That feels tiny, and it is. But that is not what the question asked. The question asked about any 2 people, not you and someone else. Any pair. In a room of 23 people, the number of possible pairs is not 22. It's 253. 253 chances for a match against 365 possible days. Suddenly, 50% stops sounding strange. The formula for pairs is in times n minus 1 divided by 2. It grows with the square of the number of people, not the number itself. Double the room to 46 people, and you don't double the pairs. You get 1,035 of them, 4 times as many. Your brain is a linear counting machine. In a quadratic world, that is where the paradox lives. So how did mathematicians deal with this paradox? They didn't. There was nothing to fix. The math was never wrong, only our feeling about it. What happened instead is that this one counterexample to intuition became one of the most useful tools in modern computing. It has a name, the birthday bound. And it's the reason password hashes need to be longer than you'd guess. In cryptography, when you want to find 2 different files that produce the same hash, what's called a collision, you don't need to check every possible hash. You only need to check roughly the square root of them. For a hash with 2 to the 128th possible outputs, you need about 2 to the 64th attempts. Still an enormous number, but vastly, vastly smaller than brute force. In 2017, Google's security team used this exact math to break SHA-1, one of the internet's most widely deployed hash functions at the time. They called the attack Shattered. It took roughly 9 quintillion computations, still easier than the alternative, and still the reason SHA-1 is now banned from every serious security system on Earth. The birthday paradox isn't really about birthdays. It's about how often coincidences happen in any system with many possible matches. The rule, if you draw items from a space of size d, the expected first collision happens after about the square root of d items, not half of d, not a tenth. The square root. That is why shuffled music playlists repeat songs faster than you expect. Why the same random usernames get picked by different users. Why déjà vu feels common. Even though every individual moment is rare, in a large enough space, pairs multiply faster than anything else. Coincidence isn't evidence of design. It's what the square root looks like when it shows up on time. The birthday paradox didn't break any math. It broke a quieter assumption that when a probability feels small, it is small. 23 people and a 50% coincidence. 2 to the 64th hash attempts to crack a cipher that looks unbreakable. A shuffled playlist that repeats itself in minutes. These are all the same math, scaled up and down. The uncomfortable part isn't the formula. It's the reminder that your brain evolved to count antelope. And there were never 253 pairs of antelope in a room. So here is the real question. How many other things in your life look like 1 in a million coincidences and are actually just the square root politely showing up on time? 23 people, 365 days, 253 pairs, and a coincidence that stopped being one the moment we learned to count the right thing. Every week, another paradox, another impossible idea that turns out to be true. Subscribe. The next one might break something you didn't know you believed.